The unsaturated hydrocarbons are converted into alkanes by catalytic hydrogenation. In this process, dihydrogen is passed through alkenes or alkynes in the presence of finely divided catalysts such as vanadium, nickel, platinum or palladium. These metals adsorb dihydrogen gas on their surfaces and activate the hydrogen-hydrogen bond. Platinum and palladium catalyze the reaction at room temperature. However, higher temperature and pressure are required with nickel catalysts. The hydrogenation reaction of unsaturated hydrocarbons using nickel at a temperature of 523 to 573 Kelvin is commonly known as Savitier and Sindun's reaction or reduction. Methane cannot be prepared by this method because starting alkene or alkyne must contain at least two carbon atoms. When an alkyl halide, usually bromide or iodide, is treated with sodium in dry ether, a symmetrical alkane containing twice the number of carbon atoms of alkyl halide is obtained. That is, when ethyl iodide is treated with sodium in dry ether, butane is obtained. This method gives alkane with even number of carbon atoms. If two different alkyl halides are taken for preparing an alkane with odd number of carbon atoms, a mixture of products is obtained. When ethyl bromide and methyl bromide react in the presence of sodium, a mixture of ethane, propane and butane is obtained. This is because the two alkyl halides not only react with each other, but they react amongst themselves also. Therefore, Wood's reaction cannot be used to prepare pure alkanes with odd number of carbon atoms because it is difficult to separate the mixture obtained. Wood's reaction doesn't give good yields of unsymmetrical alkanes, that is containing odd number of carbon atoms. However, both symmetrical and unsymmetrical alkanes can be prepared in good yield by Corey-House reaction. In this reaction, the alkyl halide is first treated with lithium metal in dry ether to form alkyl lithium, which is then allowed to react with cuprous iodide to give lithium dialkyl copper. Lithium dialkyl copper thus obtained is treated with suitable alkyl halide to give desired alkane. Alkyl halides, except fluorides, are reduced to alkanes by suitable reducing agents. For example, with zinc and HCl, that is methyl chloride plus hydrogen, and presence of zinc and HCl forms methane and hydrogen chloride. Similarly, ethyl bromide reacts with hydrogen in zinc and HCl, produces ethane and HBr. With hydrogen in the presence of platinum or palladium, that is ethyl bromide plus hydrogen in presence of palladium and platinum yields ethane and HBr. Halogen hydrides alkyl halides can also be reduced by hydrogen iodide in presence of red phosphorus, that is ethyl bromide plus hydrogen iodide in presence of red phosphorus at 423 Kelvin temperature. Ethane is formed. By zinc copper couple and ethanol and zinc copper couple reacts to form zinc ethoxide. Then ethyl bromide and hydrogen reacts to form ethane. Now alkane can also be formed by the use of Grignard reagent. Alkyl halides react with magnesium metal in diethyl ether to form alkyl magnesium halides. The alkyl magnesium halides are called Grignard reagents. These are highly reactive and can be easily decomposed by water or alcohol to form alkanes. For example, ethyl bromide plus magnesium in presence of dry ether forms ethyl magnesium bromide. When ethyl magnesium bromide is treated with water, it forms ethane and hydroxy magnesium bromide. Alkane can also be formed from carboxylic acid. Alkanes can be prepared from carboxylic acid by decarboxylation reaction and electrolysis. Decarboxylation reaction: when sodium salt of monocarboxylic acid is heated with soda lime. Soda lime is a mixture of sodium hydroxide and calcium oxide in the ratio of 3:1. At about 630 Kelvin, alkane is formed. In this reaction, a molecule of carbon dioxide is removed from carboxylic acid, and therefore the reaction is also called decarboxylation. It may be noted that the alkanes formed contain one carbon atom less than the carboxylic acid. Alkane can also be formed from Kolbe's reaction of electrolysis. When an aqueous solution of sodium or potassium salt of carboxylic acid is electrolyzed, alkane is evolved at the anode. First, potassium acetate ionizes to form acetate ion and potassium ion. Now acetate ion, being negatively charged, goes to anode and releases two electrons to form CH3COO. When CH3COO forms ethane, CH3CH3 and CO2.